So I wanted to review this problem about Newton's third law. So we've got the car towing a trailer, and when you're solving Newton's third law problems, you have to decide what's going to be your system. And if we're trying to find the acceleration of the trailer, which is the first part of the problem, then to find the acceleration, what it makes sense to do is to consider the whole thing as one. If you don't do that, then what you end up with is you have a situation where the tension forces are not balancing each other out. So to show that, what I'm going to do is I'm going to start by just drawing a free body diagram of the two things, or a system diagram, I guess, of the two things connected together. So what we've got here is we've got the trailer, and then we've got the car. And these two items are joined together by this coupling that's in between them, shown here. And the coupling has tension forces. There's a tension force backwards on the car, and there's a tension force forwards on the trailer. And these two forces are action-reaction pairs. It's a pair of tension forces. In addition to that, we've got the applied force forwards from the engine, and then we've got two frictional forces backwards, one on the car and one on the trailer. So there's quite a few forces involved here. But the important thing are these tension forces in here. You have two tension forces that are equal in size and opposite in direction. So if we consider our system to be the entire thing, the car and the trailer, then those two tension forces will cancel out and we'll be able to find the acceleration. So in this case, what we're going to say is that our system is the car and the trailer. And if the system is the car and the trailer together, then what we want to do is we want to see what is the net force on the car and trailer together. So now what we do, as we always do with these problems, is we apply to this situation F net equals ma. So what is F net? And that will enable us to find m acceleration. So the net force is the sum of all the unbalanced forces. Well, what unbalanced forces have we got? We've got the applied force forwards, and we've got two kinetic friction forces, both backwards. And the tension forces are not there anymore because they have cancelled each other out. So we should, let's just stop here, pause for a minute, and draw a proper free body diagram for our system. So we're now considering the whole thing to be a single thing, single item. We've got the applied force forwards. We've got some frictional force backwards, which is the sum of two frictional forces. We've got the gravitational force down and the normal force upwards. So let's just label those things. So the normal force and the gravitational force are balanced, and we've got the applied force, and we've got a kinetic friction force, which is the sum of two kinetic friction forces backwards. Let's put a sign convention on, so we'll say right as positive, and we'll say down as positive. That'll enable us to get the directions correct when we put in the signs right when we put in the numbers. So the applied force is 3200 newtons forwards, and then our two friction forces are negative 300 newtons because they are opposing motion. Friction always opposes motion. So that's our forces, and that's going to equal to m. The mass is the whole thing, so 2500 kilograms times a. A is the unknown quantity, that's what we're trying to find. So if I do 3200 plus negative 300 plus negative 200, I'm going to get 2700 equals 2500 A. So I divide both sides by 2500, and A then comes out to be 1.08 meters per second. It's a vector quantity as shown by the vector symbol, and so we'll say forwards. It's a positive value, so it's forwards. So what's happening is that since the car, we consider the car to be moving to the right, it's also accelerating to the right, so it would be speeding up in this case. So that part's not too difficult, and we always use the whole system when we're finding the acceleration, once again, so that the tension forces cancel. Now let's take a look at the second part of the problem, which is to find the tension in the coupling between the tractor, the car and the trailer. So if we were to consider both objects in part B, those two forces would of course cancel each other out, and if the forces cancel each other out, the tension forces, then we can't find it. So for part B, what we need to do now is consider our system to be just the car or just the trailer. So let's say just the car. You could do it with just the trailer, you'll see that you'll still get the same answer. So now we want to draw a free body diagram just for the car. So what forces are on the car? We've got the applied force forwards, we've got some kinetic friction backwards, and not as much as before, because now we're just considering the car, and then we've still got the normal and gravitational forces, which are balanced. So there's my normal force balancing my gravitational force, and then I've got my applied force and my kinetic friction force there. Let's put my sign convention on. So again, I'll say right is positive, down is positive. And once again, we apply Newton's second law. Only in this case, it's not the acceleration that's unknown, it's part of the net force, which is unknown. So we start off with Newton's second law, as always. Now, what is the sum of the unbalanced forces? Well, which forces are not balanced? The two forces that are not balanced in this case are the applied force and the kinetic frictional force. So, plus the tension force backwards. So there's a tension force here applied backwards on the car because the trailer is pulling backwards on it. So that's the net force, and that's equal to ma. So now we can start putting in numbers. So applied force is positive 3200. The kinetic friction force on the car, just the car on its own, was 300 newtons. So negative 300 newtons. The tension force we don't know. The mass we do know, it's for the car, so it's 1500 kilograms, and the acceleration was 1.08. So what does that give us? 3200 plus negative 300 plus the tension force is equal to 1500 multiplied by 1.08. So what does that come to? Just got to calculate that. So we have 1500 multiplied by 1.08, that's 1620. So the tension force is 1620 minus 3200 plus 300, and so that's, what does that come to? That's 1620 minus 3200 is 1580, negative 1580, plus 300 is negative 1280 newtons. I think that's right. Let's just check it. 1620 minus 3200 plus 300 is 1280 newtons. We get a negative value because the tension is opposing the direction of motion, which is to the right. So we can leave that as a negative sign. It's usually when we're finding the tension, we're just finding the size of it anyway, because whether you consider it to be the tension forwards or the tension backwards determines the sign. So 1280 newtons would be correct answer. I actually only have 3 significant figures here, so I should really write 1.28 times 10 to the 3 newtons for the tension force. Again, if you use the other object, you should get the same answer. So important concept here is that when you're finding the acceleration, you consider the whole system, and when you're trying to find the tension forces, you have to consider just part of the system, otherwise those tension forces will always cancel each other out.